Welcome to the lesson video on regression splines and local regression. In this video, we're going to talk about splines and local regression. So what is this regression spline? Regression spline is when we allow a spline function in our f of hat. So we're going to approximate the relationship between our inputs x and our outputs y using splines. And we're going to talk about, we'll introduce splines in a minute and talk about what they are. And when we do local regression, we're estimating the f hat function using points xi, so points in our training data that are near or local to the point x where we want to approximate this function. So we'll talk about how to do that as well. Why would we do these things? Splines are piecewise polynomials that we'll see have some nice characteristics that make them smooth, and thus they allow flexibility while we can still control the variance. And local regression is effectively non-parametric. So there's a lot of flexibility in local regression, so we can model complex relationships if the data is dense enough, and that can be a big if. So let's look at a couple of types of splines. So a spline is just a piecewise polynomial function that transitions smoothly between intervals. And so let's look at this first plot where it says piecewise cubic. So we've taken the domain age and split it into maybe 15 to 50 or 20 to 50 and then say 70 out to 80. So when we say a function's piecewise something, we mean we've subdivided the domain into a couple of pieces and we're going to have separate functions on each of those pieces. And so piecewise cubic means we split the domain into two pieces and we're going to train two cubic functions. And so there's this one on the left and a separate cubic function on the right. There's a serious problem here looking at this, and the functions don't match in the beginning, which visually is kind of disturbing, and looking at it seems to be overtraining to the data just to the left and just to the right of that 50. So we might say, well, we'd like cubic functions, we like that flexibility, but we want them to meet together nicely, and so that would be shown in this next plot, continuous piecewise cubic. So we've done the same thing. We've subdivided the domain into two intervals, and we have a separate cubic on each interval. And then at this place where those intervals meet, things look better, but they still don't look great. Visually, we can see that there's some sort of a bit of a cusp there, or there's something going on that we don't like. And so just a bit of terminology, when we divide the interval in these points where the intervals meet, those points are called knots. So when we say we have k knots, we mean we have k places where we've got intervals meeting each other. So let's look at the next function on our list here, our cubic spline, or our next plot here, the cubic spline. And let's give a definition for the cubic spline. A degree d spline has degree d polynomials on each interval with continuity and the derivatives up to d minus 1. So for cubic means degree 3. So we've got a degree 3 polynomial on each side. And at this point where they meet, they have the same value, making them continuous, same first derivative and same second derivative. So that makes them transition smoothly across that interval. So cubic splines are very nice things to work with. And we can think about the degrees of freedom here. So degrees of freedom is how many parameters we have to estimate. Up here, let's start with a piecewise cubic. We had to estimate 3 parameters, right? It's, 4 parameters. Coefficient for your 0th order, coefficient for your 1st order, coefficient for your 2nd order, and 3rd order for your polynomial, right? Those are the 4 coefficients that go into defining a cubic polynomial. On this side we have 4, so total up there is 8. Down here, now let's look down to the cubic spline, we have a 3rd degree polynomial on the left side, so there's 4 coefficients there, and on the right side we have a 3rd polynomial as well. But at this knot, they have the same 0th order, 1st and 2nd order derivatives. So that means we would eliminate 3 of those degrees of freedom. So our net degrees of freedom is 4 plus 4 minus 3, which would give us 5 degrees of freedom there. In general, a cubic spline with k knots has 4 plus k degrees of freedom. So the example we just walked through, there's 1 knot, and so we have 4 plus 1. So we lose degrees of freedom, which is a good thing at those transition points, because the having those derivatives makes it so we don't have to determine as many coefficients. This last plot shows us a plot of a linear spline. You can see why it's not as nice as the cubic spline. It's not a terrible thing to work with, but there what it is. We've got a linear function on each interval, and they meet where they meet. They're continuous, but clearly not the flexibility of the cubic splines. So cubic splines are a good general spline to use for nonlinear regression. There's one more improvement that we can do on the cubic spline and make it what's called a natural cubic spline, which will improve things a little bit. So looking at our definition here, a natural degree D spline is a degree D spline that is linear on the outermost intervals. So this is the key part, that it's going to be linear on the outermost intervals. So here's our outermost interval in this example. We have 3 knots. So one interval is around 20 and the other goes maybe 60 to 80. And if you look at the behavior of these two different splines, in red we have the natural cubic spline, which is what we're defining here, in the cubic spline, which is what we defined on the previous slide. The natural cubic spline, when you go down and you look in the outer areas, you can see it when you look at the standard error, but you can also see it when you look at the behavior. There's some overtraining that occurs in the cubic spline, the natural cubic spline, because it's linear on those ends, is forced to be more tame. And part of the reason you get that on the outer ends and not the middle are tied down with these what are called boundary conditions at each of the knots. And so that controls the behavior across those middle intervals. And so making things linear in the outer intervals controls against overtraining or extreme behavior. So a natural cubic spline is really a good tool to use for nonlinear regression. And so here's an example of a natural cubic spline on the wage data. So we've seen this data in a couple of different times with our polynomial regression. And so what we have here looks like a very nice regression on the wage data. It's very flexible, but it's not doing anything that's too extreme out at the ends. It's not wiggling too much across the middle. It seems to be behaving less nicely. On the left side is a regression. On the right-hand side is a logistic regression on this probability that this is true, that the wage is greater than 250 based on the age. And one more thing, the knots, we haven't talked about how they're determined. They're optimized within whatever software. They're picked automatically. You don't have to pick those. We don't need to get into how they're determined. A smoothing spline is the other type of spline that would typically be used. So a natural cubic spline or a smoothing spline. Smoothing spline is defined here. We create a spline first with a knot at every point, right? So that is going to have way too much flexibility, but then we're going to smooth it down to some lower degree polynomial. And so the process of smoothing, we don't need to get into it in this video, but there's a process of smoothing that takes that high degree polynomial with a lot of degrees of freedom and then smooths it down. And then the level of smoothing or the degrees of freedom you end up with is determined using cross-validation. And so in this plot on the right-hand side, we have a 16 degrees of freedom spline shown in red. And if you look at the plot, you'll see that the red tends to wiggle up and down more than the blue, and we have in blue a 6.8 degrees of freedom smoothing spline that's been smoothed, and then that 6.8 degrees of freedom was determined using leave one out cross-validation, and we see we appear to be getting nice results. Okay, last topic is local regression. In local regression, we're going to estimate f hat, our relationship between input and outputs, at each x. So for a particular x value, we're going to estimate it using points xi that are local or nearby to the x. And so these two plots, left and right hand, we're showing local regression, and we're showing the computation of the f hat function near two different x values. And so on the left hand side, there's an x that's, I don't know, 0.6 or something, and on the right hand side, there's an x that's maybe 0.42 or so. And then this is showing us how the value of f hat is chosen at each of those points. And so let's look at the plot on the right-hand side for a moment. So in blue, we have the actual function f that was used to generate this data. This data was generated by taking that blue function and then adding some noise to it to get the data points we have shown in the circles. And then the orange curve is the effect of local regression using this data. And we can see it's doing a pretty good estimation. And it's a little wiggly in places, and out at this extreme where the data is less dense, it's wandering away from the actual f function, but it's not bad. And so let's look around this input x, that's like 0.42 or so. So what's going on here? We have these red circles. Those are the data points that are going to be used in estimating the regression value for this x equals 0.42. And so there's some interval around 0.42, and we're going to take every x value that's in that interval. Take the data points for all the x values in that interval. So it's 0.42, maybe plus or minus 0.05 or something. And the data points that are going to be used for regression are shown in those red circles. This gold bell curve shows us the weights that are going to be put on those data points. So this is a weighted regression, and we're doing a linear regression around that 0.42. That's what this line is telling us. We're taking all those red points, we're estimating this line here, doing a linear regression where the points are weighted by their distance away from the 0.42. So you can see that in this picture on the right, and in the picture on the left you can see it for a different value of x. And so that's local regression. Has a lot of flexibility, tendency to overtrain if particularly if the data is not dense enough. Okay, so review of splines and local regression. What are they? Spline regression is where we allow these spline functions as f hat. Local regression is where we estimate f hat using points that are local to our input. Why do we do this? Splines allow flexibility, but they allow also a fair amount of control, particularly the natural spline, on the variance. And so primarily you'd want to try, as a first recommendation, as with anything, test a bunch of things, but a good start would be using a natural cubic spline or a smoothing spline in your nonlinear regression. And local regression is non-parametric, has a lot of flexibility. It's effectively non-parametric. And it can model complex relationships between inputs and outputs if the data is dense enough. Thank you very much for watching.